back to the lecture series on bioelectrochemistry. So, we are on to the 19th lecture, which is our fourth lecture of the fourth week. So, as of now we have talked about ion selective electrodes and change in potentials. We have talked about metal electrodes. I have given two examples, one of the glass electrode where the pH measurement is being done. Then we talked about the ion selective compounds like valinomycin, which could be used for detection of potassium ions. And there are several such ion selective molecules available in nature, which could be exploited to develop ion selective membranes, which eventually could be coupled with electrochemistry setup to know the unknown concentration. And these are some of the very potential areas of biosensors, what I wanted to highlight to give you a glimpse. Today also we will, next two classes also will be our, essentially the last two classes will also go on those application lines of analysis of biological molecules using electrochemistry technique. So, today it is our lecture 19. This is week 4, lecture 4, W4 L4. Okay. So, one of the example what I wanted to give as part of the redox titration is redox indicators. What are redox indicators? Redox indicators are compounds that change color when it goes from its oxidized to its reduced state. Oxidized to the reduced state, this redox indicator will be changing its color. The indicator of ferroin changes from pale blue to almost colorless, pale blue or almost colorless to red. Okay. So, oxidized ferroin is which is pale blue in oxidized state. As soon as it gets reduced, so it changes to red. So, in other words, what is happening in ferroin is iron, which was in Fe3 plus state, is getting losing an electron, become Fe2 plus, and because of that reduction reaction which is happening here, this is red in color, whereas Fe3 plus, which was pale blue or almost, and this molecule is essentially, when you talk about the ferroin, ferroins are something like this. Okay. So, you have a nitrogen out here, you have a nitrogen out here, you have iron 3 plus. This is what ferroin molecule looks like, and as soon as it becomes Fe2 plus, it becomes red. So, this is a very interesting situation. So, if you look at this reaction, so what is happening? Oxidation, oxidized molecule plus electron become getting reduced. Now, if you see the left and the right hand side, you can actually write an equation on this. E is equal to E0 minus 0.05916 upon n, which is the number of electron. So, the log of in the reduced state and in the oxidized concentration. Based on that, you can actually calculate what is to predict the potential range over which the indicator color will change, and that is what the Nernst equation, the basic equation what I told you. And you could have many such situation where Nernst equation could be used, and I am just giving you some of the examples which will help you to realize that there are several ways you can do it. Similarly, you can do it using cerium, which has been done several times, C4 plus and C3 plus. So, cerium, those of you who do not know cerium, if you look at the lanthanide series, the second atom in lanthanide series is cerium, and cerium in its nano state remains in two different oxidation states, C3 and C4, and it can autocatalytically shift from C3 plus to C4 plus. There is an autocatalytic shifting which happens in the narrow state, in the nanostate. Now, cerium has another very interesting property. Cerium 4, this compound is yellow in color, and this one is a white or colorless kind of situation. So, this is a drab whitish color. Okay. Now, say for example, if C4 accepts an electron and gets reduced, then it will become C3, and similarly if C3 loses an electron, it will become C4, right. So, you can actually use this assembly cerium to see the change in color to figure out how much electron is being transmitted, and if you could connect it to a potential using a voltmeter, you can actually calculate this, and oxidation of C4 plus. So, C4 plus electron making C3 plus, and if you look at, there are different potentials which could be measured using it. Similarly, oxidation with potassium dichromate, and then you have another one where you have a lot of sensors which are being using iodine, which is iodine aqueous. If you look at it, iodine aqueous, iodine plus iodide, I3 minus, which is triiodide. So, this is another indicator where iodine has been used as an indicator. When a reducing analyte is titrated with iodine to produce I minus, the method is called iodometry. In iodometry, an oxidizing analyte is added to excess I minus to produce iodine, which is then titrated with standard thiosulfate solution. So, molecular iodine is only slightly soluble in water, okay, but its solubility is enhanced by complexation with iodine. Okay. So, another process which is being used for redox titration is iodometry. You can use iodometry. So, there are several ways you can utilize your basic knowledge of chemistry for different kind of sensory apparatus. Okay. Now, from here we will move on to a much more interesting platform where we will talk about, as of now what we are doing, we are writing everything in terms of potential difference. Okay. Now, we will talk about something where we will talk about a technique which is termed as amperometry. Amperometry. And what is amperometry? And amperometry, we measure electric current between pair of electrode that are driving an electrolysis reaction. In amperometry, we measure electric current between a pair of electrodes, that are driving an electrolysis reaction. So, now we are talking about the current measurement, and interestingly, the measurement of dissolved oxygen is being done by an amperometric technique which is called the Clark's electrode. Okay. So, now if you remember when we talked about in the second class, let us go back what we promised each other, what we are going to do. Now, look at it. So, we talked about, we have already shown how potassium could be measured. We talked about how pH could be measured. Now, we are into oxygen, and it will be followed by the glucose. Okay. We are talking about the Clark's electrode now. So, the Clark's electrode talk about it, is widely used in medicine and biology to measure dissolved oxygen by amperometry. It was discovered, or it was fabricated by Leland Clark, who invented the electrode, also invented glucose monitor, what we are going to talk next, and the heart-lung machine. Okay. Now, here also we will exclusively talk about the cathode and the anode reaction. Okay. So, basically it consists of a glass body of the microelectrode, okay, with a very fine point. So, do not get worried about it. Let us look at the reaction, what is happening at platinum AU, which is the gold cathode. The reaction is this: oxygen plus 4 proton plus 4 electron, leading to the formation of 2H2O. Okay. Similarly, at AgCl anode, we have 4 Ag plus 4 Cl minus 4 AgCl plus 4 electron. Okay. A Clark's electrode is calibrated by placing it in a solution of known oxygen concentration, and a graph of current versus oxygen is constructed. Okay. So, basically based on the oxygen concentration, your current is going to change. Okay. The electrode also contains a silver guard electrode extending most of the way to the bottom. The guard electrode is kept at negative potential, so that any oxygen diffusing in from the top of the electrode is reduced and does not interfere with the measurement of oxygen diffusing through the silicon membrane at the bottom. And similar electrode has been detected or have been formulated for detection of NO, which is another biological component, hydrogen sulfide and carbon monoxide. So, what it is essentially doing is, we are measuring the current using the amperometric technique, by virtue of which one can figure out what is the what is the concentration of oxygen which is dissolved in the analyte. And you could see where you are talking about the electron. If this oxygen concentration, now if you at the cathode, where you are actually, if this goes up, automatically your current is going to go up. Okay. So, this is the fundamental basic of where we are doing current measurement instead of voltage measurement. So, in that same line, we will talk about a next analyte, which is electronic nose. Electronic nose are basically, in the old days, the chemists prided themselves on their ability to identify compound by odor. So, essentially what we are talking about is, there are vapors which bound, just like we talk about oxygen, you could have several volatiles which bound to a selective membrane, and binding of the volatile could be detected in terms of the change in electrical conductivity. There are electric nodes which people are working across the world, especially in the defense sector, where they use amperometry technique. From here we will move on to the glucose, blood glucose monitor. So, again the important part is for you to understand the reaction. So, what is happening? So, it is not the design of it. So, most of the people who are using blood glucose monitor are diabetic patients. So, many people with diabetes must monitor their blood glucose sugar levels several times a day in order to control their disease and decide when to take the insulin injection. Okay. So, again our reference is AgCl. So, you have the glucose molecule, what you are trying to measure is the glucose concentration, right. Here you have the glucose, the OH, H, OH, CH2OH, O, you have hydrogen, you have hydroxyl, you have the OH, and you have the OH there. Okay. just purposefully labeling this H plus oxygen in the presence of glucose oxidase, it forms gluconolactone, which is a compound like this, which is a gluconolactone and CH2OH. Rest all remains the same, H, OH, 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 okay, plus H2O2, and that is why I label those. Okay. So, which is hydrogen peroxide, and this is gluconolactone. Okay. In the absence of the enzyme, the oxidation of glucose is negligible. Okay. So, basically glucose is getting oxidized. The early glucose monitor measured the H2O2, which is being liberated here. They measured the H2O2 by oxidation at a single working electrode, which is held at positive 0.6 volt versus AgAgCl. Okay. This was the reaction, which was H2O2 oxygen plus 2H plus 2 electron. So, reaction at the working electrode 1. The current is proportional to the concentration of H2O2, which in turn is proportional to the glucose concentration. So, essentially current is proportional to the concentration of hydrogen peroxide. So, early glucose monitor measured the H2O2 and by oxidation as a single working electrode, which in turn is proportional to the glucose concentration in the blood. So, one of the major problem which it faced was these kind of monitors, their response is dependent on the concentration of oxygen. Okay. One of the problem with this early glucose monitor is that the response dependent on the concentration of oxygen in the enzyme layer. So, this has to come close to the enzyme layer, and here is the enzyme glucose oxidase. In the presence of glucose oxidase, this is only going to happen. If the oxygen concentration is low, the monitor respond as though glucose concentration is very low. A good way to reduce oxygen dependence is to incorporate. So, how you can do this is in a different way, because this enzyme will act when dependent on the response. Glucose monitor is that their response dependent on the concentration of the oxygen in the enzyme layer. So, this oxygen has to be on top of this enzyme layer. But now, if the oxygen concentration is low, the system will show as if there is low glucose. So, you are totally dependent on oxygen for this reaction to happen. Now, one way is that oxygen is nothing but an electron donor. If some way or other you can substitute oxygen with something else, another mediator. So, what people did after that, they use the glucose came as it is, plus they use something called a 1 prime dimethyl ferrocenium cation. Dimethyl ferrocenium cation. So, which is an ferrocenium, as you could see, this is basically iron which is present there, CH3, CH3 plus. Now, in the presence of glucose oxidase, this particular compound becomes CH3, CH3 and Fe, and what is happening here is that glucose plus 2 dimethyl ferrocenium cation, which is acting as a mediator in the presence of glucose oxidase, which is in, you have gluconolactone lactone plus you have 2 of this 1 prime dimethyl ferrocene, okay, and plus 2 H plus. So, it forms 2 protons which are getting generated. The mediator consumed in the reaction is then regenerated at the working electrode. So, what is happening is that at the working electrode, this ferrocenium, which is dimethyl ferrocene, 1 dimethyl ferrocene which is produced. So, 1 dimethyl ferrocene, so what is being liberated out CH3 Fe CH3 2. So, this is 1 prime dimethyl ferrocene. So, this dimethyl ferrocene is now you give an electron to it at the working electrode. So, you are basically injecting current to it and again make it this compound dimethyl ferrocenium cation. So, the amount of current what you are injecting to make this product which is getting generated here, out here you have that. So, you are making this reaction dimethyl ferrocene. So, the way you are doing it is very simple, think of it. So, you have the glucose, you have oxygen, you have glucose oxidase and you are making gluconolactone, and in that process you are producing H2O2. Now, you are giving H2O2 some way to dissociate H2O2 by injecting current. So, amount of H2O2 is essentially on the working electrode is telling you how much glucose is present. It is an indirect measure. So, you are injecting, you are keeping it at a certain voltage and measuring the current, okay. And based on that you are calculating how much it. So, if you have 2, you have 4. So, automatically the current is going to tell you how much current you are measuring. Okay. Similarly, here what you are doing, instead of, because we realize that glucose oxidase needs a coating of oxygen on top of it to work. If there is a lower oxygen, it will show low glucose, which is not true. So, instead of oxygen, we picked up a mediator which is in the form of dimethyl ferrocenium ion cations, which is this one, and dimethyl ferrocenium cation become dimethyl ferrocene, and then dimethyl ferrocene is further on a working electrode transformed back to dimethyl ferrocenium ion cation, and the amount of current which it is showing or which has to be injected into it will tell you how much dimethyl ferrocene has formed with respect to how much glucose was present there. Okay. So, it is kind of an indirect measure of calculating the glucose concentration. So, this is how you can use amperometry techniques to understand the concentration of different kind of biological analytes which are present or which regularly one needs to take care in the hospitals. Okay. So, I will close in here, and in the next class we will talk about some of the techniques where protein redox chemistry is being studied using different voltammetry techniques. Thank you.